I tried to parse a raw log file the other day, just a few gigs really, and I foolishly tried to load the whole thing into memory at once. My terminal completely froze up, the fans just spun up to takeoff speed, and I actually had to hard reboot the whole machine. It was a very humbling reminder that my laptop definitely has
Oh
limits.
yeah, it happens to the best of us. That that out-of-memory error is pretty much a rite of passage at this point.
It definitely is. And it set the perfect stage for today's deep dive because we are tackling that classic system design interview question. You have 5 terabytes of text data. How do you count the total number of words?
Right, and this isn't just some abstract math problem. It's really the ultimate litmus test for understanding distributed computing and failure states and, well, just the whole evolution of big data tools in general.
Exactly. And before we architect the whole solution here, a quick shout out to our partner Embersilk because, handling 5 terabytes is one thing, but actually making it useful for you is quite another.
Yeah, that's where EmberSilk really comes in. If you're looking to integrate AI agents for training or automation or even software development, they help you uncover where those agents can make the absolute most impact for your business or personal life.
Definitely check them out at embersilk.com for all your AI needs. All right, so back to our 5 terabytes. Obviously, we aren't doing this on a single machine, right? Not unless we want to literally wait a decade.
No, definitely not. This is what we call embarrassingly parallel territory. The data is just way too large for one disk to read efficiently, let alone one CPU to process. So we take that 5 terabytes and split it into manageable chunks, usually these 128 megabyte blocks, and we distribute them across a whole cluster of standard machines.
Right, so we're giving a stack of books to like 20 friends, and they all count their individual stacks. Then you just add up their final numbers at the end. That's the classic map and reduce process, right?
Exactly. You map the local counts on each machine, so you're tokenizing and counting right there. That minimizes your network traffic. Then you just reduce or aggregate those local results into one massive global sum.
So the theory is simple enough, but the real question is the tech stack. I mean, historically, this is Hadoop's backyard, right?
Yeah, Hadoop MapReduce is that reliable disk-based workhorse. It reads from the disk, does the map phase, saves intermediate results back to the disk, and then reduces. It's absolutely bulletproof,
Yeah.
but all that constant disk I/O makes it a bit sluggish compared to modern standards.
Which is why I imagine most engineers today would immediately reach for Apache Spark. It's the in-memory speed demon. But here's the catch. 5 terabytes is massive. Even if we spin up a 20-node cluster, aren't we risking total memory saturation?
That is the critical trade-off you have to consider. Spark tries its best to keep everything in RAM, which can be up to 3 times faster than Hadoop. But if your data doesn't fit in memory, Spark has to spill it to disk anyway. Suddenly, your big speed advantage just evaporates.
Plus, counting words is fairly computationally light anyway, right? The CPUs aren't really sweating here. It's the hard drives that are doing all the heavy lifting. Spot on. This specific job is heavily I/O bound. The real bottleneck is just how fast the physical drive heads can read the data. So on a standard 20-node setup, you're probably looking at maybe 30 to 60 minutes. And that's regardless of whether you use Spark or Hadoop because the disk speed acts as the ultimate governor.
The devil is always in the details, though, because even just saying counting words implies that we agree on what a word actually is.
Yeah.
If we just lazily split the text by space characters, we're going to have a really bad time.
Oh, absolutely. Tokenization is exactly where interview candidates usually trip up on this question. You have to handle punctuation and emojis and different text encodings. Like if you accidentally split a multi-byte UTF-8 character, say a kanji symbol, right at the 128 megabyte block boundary, you literally corrupt the data.
Wow, yeah, you need robust logic to handle those boundaries gracefully. And then there's the harsh reality of hardware. If we run this job on 20 nodes for an hour, statistics basically guarantee that something is going to blank, a drive fails, or a network packet drops. But that right there is the pure beauty of this infrastructure. It's so inherently optimistic. The system assumes failure is possible but temporary. If a node just goes dark, the master doesn't panic. It automatically retries and assigns that specific task to another worker node. No need to restart the whole job.
So it's totally self-healing. I love that. What about hotspots, though? Like data skew, where one node gets stuck with a super dense block while the others just sit idle?
That can happen for sure, like one friend getting a massive dictionary while everyone else gets a kid's book. But modern sharding algorithms handle that load balancing remarkably well these days.
It really is incredible when you step back and look at it.
It is. I mean, we focus so much on the simple act of counting. But the real magic is the underlying infrastructure. It allows humanity to process information at a scale our brains literally cannot comprehend. It turns an overwhelming mountain of chaotic data into this beautifully solvable puzzle.
It's a brilliant reminder of how ingenious we can be when we build resilient systems that work together to solve big problems. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.